This is precept 5. Let's talk about the binary search trees as our first problem here. So what's a binary search tree? Binary search tree is a binary tree such that the left subtrees are less than the root and the right subtrees are greater than the root. And binary search trees cannot have duplicate elements. So assuming that we have 3 keys, our goal is to write all the possible binary search trees. We also know the order of these keys, that A is less than B, less than C. So let's see how many trees can we draw. So in this case, we can say, let's draw the one that makes the most sense, which is a nice balanced binary search tree of this shape. And then you can put the C here, and then B, and then A. Or you can put the A and the B and the C. Or you can put the A, this shape of a tree, where you put the C and the B on this side. And then this shape of a tree, where you put the C, and then you put the A and put the B. So we notice that we are able to get 5 trees when n equals 3. Now we can ask a question, what makes them binary search trees? How do we know that we are binary search trees? Now one can say we can go through each node and check the condition that left is less than the root and right is greater than the root. But that would be too difficult to do for each node. So one of the things you could do is that you could do order traversals on this. For example, you can say, okay, let me go traverse this binary search tree in order. This means I go to the left and then the root and the right. So I would produce the sequence ABC. Same thing here. If I go left, I have to go all the way to the left. That would be A. Go back to the root, B, and then go back to the root of that. That's C. Same thing here. Go to the left. There's nothing on the left, so print the root. And then go to the next subtree, right subtree. There's nothing here, so we print B, C. Now you can see that if you continue this, you would get ABC for all of them. So this kind of gives us a very interesting observation that says that if you just have a binary tree, there can be lots of binary trees that I can create from this set of keys. If you have a binary tree, and if you traverse the tree in order, and it produces a sorted sequence, and that implies that it is a BST. So it's a good test to see if someone gives you a binary tree, you traverse the tree in order, and you get a sorted sequence, it must be a BST. If you don't, it's not a BST. Now we can ask the question, what's the complexity of finding whether a given binary tree is a binary search tree? I guess the answer lies here. What is the complexity of doing in order? Now one can say that in order traversal means that you have to touch all the nodes. So it's got to be at least linear time. But since we know an algorithm, which is in order traversal algorithm, recursive one, that can do this in n time, we say that we have a optimal algorithm for doing in order traversal in big O of n. So hence, given a binary tree, I can test whether the tree is a BST in linear time. Now let's take a look at the part B of this first question. So the part B says that an in-order traversal of a binary tree is obtained by recursively visiting left and then processing the root and visiting the right subtree. The way I try to remember in order is to say that if you have an expression which is an infix expression, and if you build a tree out of this, we call this expression trees. Now you can see that the in order is like an expression tree that can be traversed in order traversal, like you do left and then the root and the right, left, root, and the right. Now the same way the pre-order is going to be a prefix notation. So the prefix notation means that if you're familiar with the prefix notation, the operator comes first, and then you have the operands. So in this case, the root is visited, and then the left, and then the right. So the in-order is left, root, right. Pre-order is root, left, right. So now what we're going to do is to write down the order of the keys in the BST in the in-order traversal. So I'm going to use different colors. So I'm going to be using blue to traverse this tree in order. So I start with the root, go to the left, because remember you have to go all the way to the left. But there's no more left here. I'm going to print this as the first node. And then once I'm finished, there's no left, process the root. Now let's process the right subtree. So in this case, I'm going to go all the way to the left in that subtree. So I would be printing E next, and then F. So I process root and right subtree. Now I need to process this, and I have to process this right subtree. In that, I'm going to process the left. There's no left, so I process the root. I'm going to process the right subtree. In there, I'm going to go all the way to the left and process this, and then finally process the root there. So that's the in-order traversal given in blue. Now, I'm going to give you the pre-order traversal in red. So the pre-order traversal goes like this. You have to start with the root, then you go to the left. In the left, you process the root, then you go to the left. There's no left here. Go to the next one, you process the root, and then you process the left. So I'm done with this subtree. Now I'm going to go to this one and say process the root first, then process the left. There's no left here. Go to this one and process the root, and then process the left. So the pre-order is given by this order where you have the red one now, the pre-order traversal. Notice that some of them have the same order, some of the nodes, but most are different. Now this kind of leads you into a nice problem. It says that, so in the previous problem, you looked at, given the graph, or given the tree, can we do the in-order and pre-order? In here, we're going to look at the opposite of that. Given the in-order and the pre-order, can you draw the BST? So what you're going to do is to think about what the pre-order gives us. Pre-order tells us what the overall root is. So I know the root of the thing is D. Now you have to assume that I don't know anything about these keys. They can be cats and dogs. Only thing I have is an ordered sequence of these keys. I do not assume anything about the alphabet here. So if I go to the in order, which is in ordered set, I will know that the left of D of this BST are the keys A, B, and C. I'll figure out how they're ordered next. The right of that would be the keys M and O. All right, so I use the pre-order to get the root, and then I use the in order to see what's to the left and what's to the right. And now, because I have grouped them, I can also use that information to group things here. So now I know the pre-order traversal of the tree that has the nodes BAC. So I can use that to get more. So in the pre-order traversal, the B comes first. So B's got to be the root. And then A is less than B, because we know that from here. Therefore, A has to be on the left. The C is greater than B from this order here, and hence C has to be on the right side. There cannot be any other configuration of these elements. Now let's make the same argument for M or N. Now because M is the one that comes first, I know M is the root. Now the next question is whether I also know that M is the smallest, therefore O and N has to be on this side. So the question is now, how do I split that node to get the correct positions for O and N? Now, one of the things we know is that N is less than O. But in the sequence, O is printed next. Therefore, O has to be here. and n hence will go to the left of that because n is less than O. And so we will have this pre-order traverse. So if you notice that if you do pre-order, you'll have D, B, A, C, and then you'll have M, O, N. If you do in-order traversal, you have A, B, C, D, and then you will have M, N, O. So hence we got the tree. In fact, this tree is uniquely determined by this order. Now, one of the things I did not mention in the previous part of the problem is this one. I'm going to go back to this one for a minute here. We got 5 trees and n equals 3. In fact, if you're curious about whether you can come up with the number of trees given n, there's something called the Catalan number, which is given by 1 over n plus 1, 2n, n. You can read about this in the Wikipedia. I'm not going to go into details here, but if you plug in n equals 5, you probably will get 5. N equals 3, I'm sorry, n equals 3, you'll get 5. So that's a nice little formula to do that. So, okay, so in this problem we did, we looked at binary search trees. We tried to determine specific things based on that. Our second problem deals with designing data structures. So you have a midterm coming up. For the midterm, we're going to have to think about how to use all our knowledge that we have so far to design data structures. Now we know a lot of data structures. We know heaps, we know BSTs, we know symbol tables, we know arrays, we know linked lists, and they all do certain things really well, but not all of them. So the question is, if you have a situation, you have to define a certain API for some notion called a generalized heap. Let's call it G heap. Now this is not a standard thing, but I think it's an important and like a useful thing to do, that you design a data structure that supports this API. So notice that in the API we have the constructor, we have a min method, we have an insert method, we have a delete min method, and we have an update method. Now, one of the things about this data structure is that we want to support all these operations in logarithmic time or better. We are not interested in linear algorithms. We are interested in logarithm or less algorithms, because we know we have to deal with large amounts of data, and unless it's log n, it's going to be really slow. Now, one can say, okay, when you're designing this data structure, what can we do? Now, if the requirements for the problem are just creating a data structure to do these 3 operations, min, insert, and delete min, we know that we have something called a priority queue. So we can call it a min PQ, right? So if you have a min PQ, you can do min, insert, and delete min all in log n time. But we have this notion called update. So this priority queue, so if you have a priority queue, which are organized by this priority, is it possible to update an element in a priority queue? So the idea would be something like this. Let's say you have a priority queue that looks like this. Say it's a min PQ. And so you have a bunch of things here. And so on, right? So now in a priority queue supports really well the finding the minimum or deleting the minimum or inserting it using a binary heap. It can do it in log n time. Now the problem is going to be if you have to update this element from 3 to 5, what can we do? The problem with the priority queue now is you cannot update this element because in a priority queue it's not random access. You cannot find this element easily. This element could be on this subtree or this subtree here. So hence you may have to go through the entire collection to find out this node that you need to change. Now that's not a good one because that's going to take a linear time to do it. So what you need to think about is a priority queue by itself will not be enough. Can we have like a binary search tree? Binary search tree, yeah, if you get a balanced binary search tree, you could do min, insert, and delete min in log n time. And if you can update the priority of an element in the log n time. Well, I guess one can argue that you have a balanced BST, you may be able to do something like this, if provided that you keep some priority. But the question is that if you do that, then will you be able to find the minimum in that time? So that may not be possible. So one of the ideas that are really important to understand is to think about the data structure we discussed in class called the symbol table. So when you think of symbol table is like a generalized array. Typically if you have an array, you have an index, and I can look at the A of that index to find the value. Now in a symbol table, this index is not an integer. In a symbol table, that thing is called a key. So if you give me the key, I can find the value. It could be an array, it could be anything. Okay, so I'm not assuming any kind of a data structure here. So the whole idea of priority queue is that you have a key value pairs stored in a priority queue. The key lets you find this index, and then it lets you find the value. So one of the goals of this thing is that it says that there's some other things that you have to pay attention to. It says that you can use additional space. So maybe I could use a min PQ and a symbol table. They are both size n, so I can use some additional space. So it'll be redundant that I will have the same thing stored here as in here, but it'll give me a fast update time. So how do I do that? So here's how I can think about this. So let's say that this was stored. This node is really a record that you have stored, where you have an item and a priority queue, a priority which is 3 initially. All right, and then what we're going to do is we're going to put the same item here as we are building this min heap or priority queue. We're going to put the same item here with that key as the item, or some part of the item, doesn't matter. And then you will have some sort of a value of this thing, maybe a reference to the item node. What I mean by item node is this node here. Remember that this node in the priority queue is some random memory space where we know how to get to because we have an address. So if you have a reference to that, so it's more like I'm creating a pointer to this, then that would be good because I will be able to do a few things here. So how does this work? So let's say that I want to update some item with the new priority. So what I need to do is first use the symbol table to find this item. So I find the item to this slot here. Once I find the item, then I get the value of this item, which is a reference or a pointer. So I follow that pointer to this node. Then this node is some random node where I know how to get to. Once I get to the node, I can change the priority from 3 to 5. All right, now I have a problem because once I change the priority, I may have to do something because I had to either sink or swim to maintain the min priority queue operations, because remember we have to do minimum, insert, delete min all in log n time. So to do that, if you look at this now, the new priority is 5, so therefore it's not balanced. I mean, it's not heap invariant, it's not satisfied, so I'm going to find the minimum of these two, which is 3, and then move the 5 here. Essentially your item is now going to be here, placed here. So it's a technique that combines 2 data structures instead of 1 to create a new data structure called a G-heap, which supports an API in very efficient time. So our third problem is about KD trees. Now KD trees are 2-dimensional binary search trees that allows us to traverse through a tree by two different orders. Now, typically we know that we can only have one key and one order to traverse through the tree. We go left or right based on less or greater. Now here we have, what if we have a bunch of points in the plane and we want to create a binary search tree to represent that? So we can call that a 2D tree. Now there are many applications in graphics and databases for 2D trees. We are looking at 2 dimensions, efficient search based on 2 dimensions. Now typically we search by 1D, but if you have to search by 2 keys, it's not that trivial to create a data structure to do that. So KD trees give you an opportunity to create data structures that can be, we can use multiple keys to traverse. Now to introduce you to the KD tree idea, I'm going to show you something simple here. So let's just say that we have a plane and we have a bunch of points. Now let's assume that these points have to be put into a KD tree, and also these points split the plane. Now why do we do that? The reason we do that, if you have a bunch of points on the plane, and if someone asks me, given a rectangle, how many of these points are inside this rectangle, I can certainly come up with a naive algorithm that takes each point, check whether it's inside, and go through all the points, and that would be big O of n. So my naive algorithm for testing how many points are inside this rectangle would be linear, but that's not good. We want to be able to get close to log time of performance. So how do we do that? That's where the KD tree comes. So here's the idea. The idea is that we look at these points and start inserting them into a tree, a special kind of a binary tree. So suppose the point A is here. So I'll put the point A there, which is the geometric thing, which I don't have it. If I'm writing a program, I don't have it here, but I do have a, I can work with a tree here for sure. Now in the tree, I make the A, the first point, this is going to be the root. And this point, I'm going to split the plane by a vertical line. So let's take the next point, B. I'm going to place the B here. Now what this means is that the point B is to the right of A, and therefore I'm going to insert the point to the right of this tree. At this point, I'm going to use a horizontal orientation to split the plane. And let's put the points, let's use a different color here. Okay, let's use this color. Okay, so let's put the point C here. Now point C says that it's to the right of A, it's to the right of A, which means you're on this one, and it's lower than B. So this means that it's less than B. So I'll be placing the point C in here and draw a vertical line. So I'll draw a line here. And so I'm done with C. And let's put the point D. Let's put the point D in here. In this case that I have, so you have your point D here. So it says that point D is to the left of A. So this means the point D will be inserted here because it's a horizontal level. I mean, this is a, so in other words, we use the X coordinates to compare things at the even levels, and the Y coordinate to compare things at the odd level. So as you go down the tree, you have to use either X coordinate or Y coordinate to compare things to determine which way to go. So in this case, I can just look at the picture and say D is to the left. So I'm going to insert the D to the left of A. And let's take another one. Let's take the point, say E. I'm going to put the E in here. All right, so I have to determine where E is going to be. So I know E is to the right of A, so I'll go this way. lower than B, so I'll go this way, and right of C, so the E has to be here. Okay, because it's an even, it's an odd level, I will have a horizontal line through E. Let's put it like this. All right. And now let's take a look at the next point, F. So the F is going to be, I'm going to randomly put this F in here, for example. Now, where do I find F in this picture? So I can say the F is to the right of A, and it's above B, so it's the right of B. So F would be here. Because it's a vertical split, I'm going to draw a blue line here to split that. Now, finally, I'm going to put let's say I'm going to put the G here. So this means that it's the right of A, lower than B, and left of C. So the G should be here. Because it is a horizontal line, I'm going to draw something here. All right, so this shows you how a KD tree is built. And as you go, the KD trees are built by comparing the coordinates. So let's take a look at how we can build this KD tree here. So I'm going to call this A, B, C, D, E, F, G. So let's start with A. A is going to be 2, 3. So that's the point A. And then I'm going to split the plane by a vertical line. So this is A. That's that, right? And then let's get B. B is going to be 4, 2. B is going to be 4, 2 here. Now B is going to be to the right of A. So I'm going to use a red pen here. So this is B. And then I will split the B by this. Now note that the B coordinates are 4 and 2. And A coordinates are 2 and 3. Now when I compare 2 to 4, I had to come right. So because I compare X coordinate at this level. So that's where the B is going to be. Now let's take a look at C. C is going to be 4, 5. So C is going to be 4, 5 is right here. So this is C. Now we have to see where the C is going to go. C is to the right of A, above B. So C is going to go here. All right. And because C is a level that's vertical, so I'm just going to draw this line here through C. And then D. So let's take a look at D. D is going to be 3, 3. So D is 3, 3 here. So here's 3, 3. So if I'm inserting this to the tree without even looking at where it's going to go, 3 is bigger than 2. So I go to the right. Now I compare 3 and 2 because I compare y coordinates at this level. And that time I go to the right, so I come to C. Now the C has the coordinates 4 and 5. At this level, I compare X coordinates. So at this point, X is smaller than this X here. So the D needs to be installed here. So therefore, D will have a vertical split. So the D point, the horizontal split, I'm sorry. And then E is going to be, let's see where E is going to go. So notice that I'm working with 1 and 5. 1 is less than 2, so I'm going to go this way and insert E here. And because it is a red line, it's an odd level. So the point E, which is 1, 5, is going to be here. I will draw a red line there. And F is going to be 4, 4. F is going to be 4, 4. So compare 4 to 2, go right. Then the next 4 is the y coordinate. 4 to 2, go right. 4 to 5. And now we compare X coordinates. So 4 to 4. Now we have an equal elements. X coordinate here is equal to the X coordinate there. So we break the tie by going to the right. So the F would be inserted here. And that would be this. So the F is going to be 4, 4. And that is going to be here. Notice that it's the above B and right of C. All right. And then finally, G is going to be 5, 4. 5, 4 is going to be the point 5, 4 is going to be somewhere here. So if you do the comparisons, 5 is greater than 2, go here. Now compare 2 and 4. 4 is greater than 2, so go here. Compare 5 and 4. Now 5 is greater than 4, go here. And the f is 4 and 4. Now you compare x coordinates. I think this, yeah, this is x, y, x and y. And compare y, 5 is bigger. So you go to the right and insert g, and that becomes a vertical line here. So it's, you can say it's the right of A, above B, right of C, and above G, right? So so where's the forgot to mark the F, so it's here's F, and here's the finally the G. It's 5 4, yeah. So this kind of this breaks a tree into splits, breaks the plane into segments. So this is how the KD tree is built. So let's take a look at the other parts of this this problem. So the next part of the problem says find these bounding rectangles for each point. What we mean by bounding rectangle is some rectangle that encloses the point. Now, the reason we do that is that if you have divided the plane into rectangles like this, some random rectangle divisions, and if you're given a search rectangle, that means you want to know all the points inside that rectangle. Now we know that this rectangle, this particular rectangle, which refer to some side of the tree. So you can say that was the left side of this tree, this whole thing, because that's the middle. Will have no points belonging to this particular thing. So this allows us to prune the entire tree. So knowing that our query rectangle does not intersect with a certain rectangle, which is really a subtree, will allow us to prune the tree. So we can do pruning in a way that we can make the search more efficient. So let's start with by figuring out what the bounding boxes are. Okay, so I'm going to do the following. I'm going to go with first A, E, and B, because E and B are children of A. I want to make a point here. Now, when I mark up the these things, so let's say that, I mean, I can do infinity, infinity, 6, 6. Let's go with 6, 6 here, and this to be 0, 0. Okay. So I'm going to think about the bounding boxes. Now, obviously, keep in mind that this could be minus infinity, and this could be plus, excuse me. This could be plus infinity, plus infinity. But for convenience, let's go with these bounds. So the bounding rectangle for A is the whole thing, or minus infinity, and plus infinity, plus infinity. E, if you look at E, E is to the left of, so here's E, I think, right? And so E happens to be the point, yeah, it's the 0.15. And we note that the E has a bounding box of 0, 0. And then the right-hand side would be 2 and 6, if you notice that, right? So that's the bounding box for E, which should be this bounding box here. And for B, now one thing you want to note is that we only had to change one element from the previous parent to get the bounding box for E. And that's really important because when you do the assignment, you have the parent information, and then you have to determine the bounding box for the children, and they can be determined based on some of the information you have in the parent. So notice that 2 is in the parent, so that gets updated. On the other hand, if you look at B, the bounding box for B would be this whole thing here. So one can say that's going to be the x coordinate 2, y coordinate 0, and then 6 and 6. So again, if you look at the difference between A and B, we only had to change one coordinate to get from A to B, the bounding boxes. So in other words, the bounding boxes for children are depending on their parents. So let's take a look at B and C, because B and C is the right child of B. So now the B is 2, 0 and 6, 6. And now what is C? Now the C is here, right? So the C's bounding box is this one here. So let me use a different color here. So this is C's bounding box. And what are the coordinates for that bounding box? So we know the following. We know the left coordinate is 2, and the this coordinate is going to be 2, and then the rest is 6 and 6. So notice that between B and C only one coordinate change. And the so the C, if you're given C, 2, 2, 6, 6, and C has two children, D and F. So let's find the bounding box for each one, D and F. So let's look at D. So D is to the left of, so the C is here, C is this thing here. So it's going to be, let me use a marker here, see if I can get this thing going. So the bounding box for D would be this one here, if you agree with me. And what that means is that the bounding box for D would be 2, 2, and the y coordinate, this would be 4 and 6. So notice again, only change 1. The bounding box for F is going to be, let me mark it up here again. It would be this one here. And in that case, the bounding box for F is going to be x equals 4 and 2, and then we will have 6 and 6. So notice that from here to here, it only changed one entry to get there. All right, so that's how the bounding boxes are found, and that's really important. And now we're going to do the problem of finding these KD trees, the queries. So how are the queries done? The queries are done like this. So one is called the range query. That means you have a shader rectangle. We're going to write R next to each of the things. Obviously, we have a 5, 4 here, which is a right child here. Okay, and so what we're going to do is that when we do the query, and so 5, 4, let me mark it up here, 5, 4. Okay, so let's do the query, and we are going to write the R next to it as we do the query. So the query says the following. Let's start with 2, 3 and see if 2, 3 is inside the bounding box. And so we consider that, I'm going to write R because we consider that. And 2, 3 is inside the bounding box. So we say, okay, we will have an iterable where we will return the 0.23 because it's part of the bounding box. Now we have to look at left and right. The reason we have to look at left and right is if you look at the bounding box of 1 and 5, which is this one here, and 4 and 2, which is this one here, they both intersect the query rectangle. So you could have points in either tree. And therefore, I have to look at 1, 5. So in this case, I look at 1, 5. 1, 5 is not inside the rectangle. You can easily check that by doing a simple middle school algorithm. So I know 1, 5 is not in the rectangle, although I had to look at it. So I'm not going to put it in here. And then the next point I look at is 4, 2. So 4, 2 is not inside the rectangle. So I'm not going to put that in there. And then I'm going to go to 4, 5, the next point. Okay, so the next point is 4, 5. Now the bounding box for 4, 5 is going to be, let's take a look at this one here. So for the 4, 2, the bounding box for 4, 2 is going to be this whole thing. And then 4, 5, the bounding box is going to be this thing here. And because it still intersects with the query rectangle, I have to consider that, although I'm not going to include 4, 5 in my set because it's not part of the thing. And then I'm going to go to the bounding box of 4, 4. So the 4, 4 is above 4, 5. So that means it's going to be this bounding box here. And because it doesn't intersect with the query rectangle, I can remove this entire thing. But I still have to look at this one here because it does intersect. So this bounding box intersect, that's the bounding box for 3, 3, intersects with the query rectangle. Therefore, I need to look at it. And I figured out that 3, 3 is included there. So that's how you find the query. Now, the nearest neighbor would be very similar. I'll give you the idea. Hopefully you can work through this. So in the nearest neighbor, what you're going to do is you're going to find, you're starting with the, now let's use different color here. So you're starting with the original point, which is 2, 3, and see how close you're computing the distance and say that's the champion distance. I have a good distance here. Now, if you look at this, one of the things that we do know is that the vertical distance from, so for example, let's take a look at this. So we're going to say, all right, we have to consider that, and we have to also consider 1, 5, right? Because we have to consider 1, 5 because 1, 5 could be this bounding box could be closer to point P than this one here. But let me just give you a simple idea that can help you understand this. Suppose this this plane is divided into many segments, and so any segment that you have refer to some subtree of the tree. Like for example, this could be a segment that we're thinking about. Now let's assume that the distance between the point P and the bounding rectangle is greater than what we have found so far. Now what that means is that any point inside this rectangle could not be closer than what we already have. And therefore we can remove or prune this entire subtree from the search query. So the whole idea here is that the bounding boxes, the distance between, the orthogonal distance between P and a bounding box, will tell us whether we can find anything inside that box or not. So for example, if you had something like this to begin with, you would be removing a lot of different things, like I don't even have to consider that, right? So this bounding box may not be, I don't have to worry about that. So depending on what order you get the points, you can remove again the bounding boxes. So finally, there's a bonus problem. I will do this anyway. The bonus problem says that given n lines in the plane, design an n squared log n algorithm to determine if any 3 of them intersect at a single point. Now the whole idea here is that you have to think about something. If you have n points on the line, there are n squared possible intersection points. N squared possible intersection points between these lines, n lines. Now these points could be P1, P2, P3, P4, P5, and suddenly you may see P1 again. So what does that mean? What that means is that 2 lines, maybe line 1 and line 2, may have intersected to create the point P1. And there was a P1 again came up when line 1 intersected with line 7. So that means line 1, line 2, and line 7 all have the common point P1. So that means 3 points intersect at the same point. So one possible solution for this one is that you would find all the possible intersection points, and then you could either do a KD tree. If you do a KD tree, you start inserting these points into the KD tree. As you insert point into the KD tree, if the point is not in the KD tree, you will insert it. If it is already in the KD tree, such as P1 and P1, that means you have found lines, 3 lines that intersect at the same point. So if you think about the complexity of the algorithm I'm just describing, if the KD tree is log n height, in fact it's log n squared height, right? Because you have n squared possible elements, but notice that the log n squared is the same as log n. So my complexity is like 2 log n for inserting something into a KD tree of n squared nodes. So because I'm inserting n squared nodes into the KD tree with log n for each one, I will have an n squared log n algorithm that can determine if 3 or more lines intersect at a single point. And so it's a simple algorithm of KD trees, but you could have done this in a different way as well. For example, you could have taken all the points and sorted out. So if you have n squared possible points, intersection points, you can sort it in n squared log n squared, but we know this is n squared log n, 2n squared log n. And hence you have, and now once you sort the points, the p1s will come together and you will know in less than n squared time that if you can find duplicate elements. So you have designed an algorithm that's n squared log n to figure this out. So you don't really need a KD tree for this, but it would be nice to have one.